session. The second session is basically going from 2% calibration and trying to get it down less than 1%. We see this in calm conditions. Most vessels will manage less than 1%, but if you want it in all conditions, then you need to have a very good calibration to actually make sure it works. Now, in front of you, hopefully you can see the screen of the DL2. I thought I would first of all show you how we do a calibration, just as I described before the break. Here I'm running a simulator, and there are simulators available on the web. This one is running on an actual system, so it manages to do most of the functionality that we need. So at the moment, I'm running a simulation of 20 knots and 1 knot sideways from the sensor. I can see that by going into the diagnostics, and here I see the sensor live information. Here you have the speed through water, 2-axis longitudinal, speed through water transversal, speed over ground longitudinal, speed over ground transversal. And then we have a high frequency. We're running on multiple frequencies, which is also running here. And this is controlled over here in this panel. We're running a simulation inside the sensor itself, which means the whole system is actually working as it should be. This is actually making acoustics at the front of the sensor and measuring it. So it's a good way to check the whole system is working correctly, even when you're in harbor or whatever. The DL2 sensor doesn't really have any problems with running in air, but we recommend you not to do it for long periods of time, but it's fine for a few hours. When we set it to sensor, then you set the speed and you press start, and it will download the required speed down to the sensor, and the sensor will send it back just as if we were actually sailing at that speed. Here you see the quality of the data coming back. Speed over ground data, particularly in shallow water, will have a quality quite high. The quality is between 1 and 9. 9 is the best. You can expect a ground signal to be 8 or 9 most of the time. Down to 150 meters. The system can actually go down to 200 meters as well. The speed through water is measuring particles in the water, and depending on the number of particles and the conditions, the quality of that signal can go right down to 3 or 4 or 5 and still be okay. What we do say is if it's going below 3, then you will start getting warnings on the system that the quality is poor. Here we have the depth being measured in the 2 beams. We have set both of them to 180 meters, which is slightly out of the range. Normally it will be less than 100 meters while you're doing a calibration. The temperature here you see is measuring 33.6. This is because the sensor is sitting next to me and warming itself up. At the moment we have no GPS coming in or heading or rotation, but if you have that coming in, and we do recommend having GPS both for the time and for position, because this will be logged together with the other data so you can see what's happening. And also heading, if you want the aft speed, the docking function working, that needs to be in as well. There are 2 inputs, so you can put them in both. So here we're seeing the system. I'll just run a self-test on the system just to see that everything is okay. Here you see the voltages are okay. The traffic on the LAN port is okay, and the sensor test is okay. To see more data, we click on the S and you can see more data. Here you see everything is okay. Traffic, not very meaningful, but it's telling you how much data is being passed around, which isn't very much in this case. And the sensor, here you can see the sensor firmware, the version, the serial number, and the currents that are running up and down to the system. So going back, we have the data coming in. We want to do a calibration. So we go into the first thing we have to do is set up the system, of course. So we go in and we need to set up the speed, maximum speed of the vessel. So here we're on 22 knots. Password is always service, easy to guess. Then you can set your speed. We'll say this vessel is going to go 23 knots max. Here you get a warning that you are going to overwrite your calibration points. So you only do this once, or if you're starting again in some way, we say that's okay. Then we want to look at the temperature sensor. Now here we go out and we look at the calibration. Here we have temperature. Here we see that the calibrated temperature is 28.6, and the temperature in this room is actually a bit cooler than that, being in Norway. So now this is calibrated correctly. Obviously, when it's in air, it's going to be slightly warmer than when it's in the water and being cooled by the water, and that will have an effect on here. So the next thing then is to go and do the calibration. Now, at the moment, I don't have GPS coming in, so I can't do the calibrate by GPS. But you see here, we're sailing at 20. Now, if we were actually sailing at 20, the GPS would also be showing a line up here at 20, and you could press the button to move the two curves. You see here, there are two curves. The green one is the speed over ground curve, and the blue one is the speed through water curve. And generally on the vessel, you will see that the speed through water curve is slightly above the speed over ground curve, and that it will slowly curve upwards. And this is due to the drag of the water underneath the vessel. This is why on large ships, we say do a calibration up the top here. And then we also want to do one a bit below 10 knots down here, because it tends to go down and then flatten out at the low speeds. So those two calibrations are important for larger vessels. We go to the manual. You see here we're looking at point number 1, but we want to look at point number 5. We see the real speed is 20.7, and these are the measured speeds to make it correct. What we can do is adjust one of these. I'm sorry about the flicker. I've just been informed. There's not a lot I can do about that, I don't think. Unless it's out there, it's maybe no. It's still. So here I will change this to 20.6. Enter, and you see down here the manual is now gone to manual, but I can put it back to default by pressing it. And if there was a C test in there, I could change that as well. So that's the manual calibration. Then we have the C test. So here we're going to sail a leg. I'm going to do this quite quickly, so I'll put 0.1 as the distance. You want to sail at for about 5 minutes. So if you're going at 20 knots, 5 minutes is a nautical mile. If you're going at 30 knots, you probably need to do 2 nautical miles. If you're only going at about 5 knots, then you only need to do half a nautical mile. You don't need to do more than that. Otherwise, it will take a long time. So here we have put in the distance, and then we're sailing up to the point. I could put it so that we stop on GPS. And then when you get to the start point, you press start. And then these values will start counting. You see GPS is not counting here because we don't have it, but the water and the ground are counting as we're sailing along. Now, as we get to the end point, if you don't have GPS, you have to do this on the chart. When we get to the end point, you press stop. You accept the leg if it's a good leg, and then you start going back again. Down the bottom here, you see the validity. The validity is how many of the points it has measured are actually acceptable through the quality standards. Here we're seeing 100% on both of them. So let's say now we get to the end, accept the leg. I do a quality control here. I look at the average speed through water. Here I clicked exactly on 1, so it's 20 knots. Average speed over ground, also 20 knots. The calculated real speed was 19.2. Now, if you have a GPS going, you will tell you the average that you got off the GPS, the minimum and the maximum average. And if your vessel is changing in speed, then you will see that on here. If it is changing more than about 0.2 from the calculated real speed and the average speed, then you should consider doing it again if you're trying to get a very good calibration. Now here you see it has calculated the point out here. It looks a bit strange, but it's because I've done doing this in simulation. But I'll say I'll accept that. So I press save. It was accepted. And then if I go back out here, we now see that the new point is in place and all of the other lines have changed as well. So if I go to speed and I look at the manual now I see that I've got a point source of C, but I can put it back again to default and then we go back to how it was, or I can put it back to how we had it in manual. Then you look at the installation angle, and here you see we've done a calibration. And because we've got the simulator going 1 knot sideways, we actually have an angle in here, and it's 2.9 degrees we see on this one. And if I disconnect the two, I can adjust this one as well. So now I'm looking at the speed to water. That one's also 2.9. And I can adjust that offset there. And I can adjust this one by pressing averaged here. And now if I go back, now you see the speed being measured is 0 sideways because we have adjusted away that angle. Sorry about the flicker there. I will now go back to the course, which isn't flickering, hopefully. Right. Okay, so to get better than 1% accuracy, the things we need to do a careful calibration. We need to start and stop when the vessel is at a stable speed and a stable course, and you need to be sailing at a stable speed and course throughout the calibration. Now, what I have seen on a number of calibrations in real life is that the vessel takes a long time to turn, particularly on the second legs, and it's still turning when you get to the start point, and you press start anyway, and you see the heading is changing throughout the calibration. Also, the speed, you maybe turn, you slow down, you need to speed up the ship again, and that can take a while, particularly on large ships. Also, if you're trying to do this in a sea test and you're trying to do it on the back of another test, like a power test or something like that, then you might have quite a long time between your legs, so that the current and the wind conditions have changed. But the main things is to have a stable course, a stable speed, and good conditions throughout. If it is really windy and a lot of waves, then you will get a worse calibration. Now, we said we have 2 frequencies in the system. We have a high frequency and we have a low frequency. The high frequency was added after a couple of years with the system, and we found out that it gave speed through water a doubling of accuracy. So by using the high frequency table, we can get an accuracy which is well lower than 1%. But this means we also have to calibrate the high frequency and the low frequency, and these are slightly different. Now, we've done this automatically within the system, but if you are having problems, it can be adjusted manually. We can also set the averaging to give an optimal performance. You might want to put it up or you might want to put it down. What you do find is that some vessels concentrate very much on maneuvering, Others just want it to be correct because they're using it while they're in transit, because they're using the system in a efficiency system, for example. So there's different needs from different vessels. We try and get the best on both worlds. So to understand why we're doing the different calibrations, you need to understand the system a bit better. Now, the difference between the DL850 and the DL2, there's a few differences really. The DL2 is basically a newer generation system. The DL850 is about 20 years old, and it was using analog technology. At that time, to do replacement cards was easier than to do soldering. They've gone on to that, but so the system has a lot of different cards that can be replaced. The DL2 only has, the whole multi-series only has 8 PCBs. The DL2 has 3 PCBs that are in use on it. So really, for service, it's just replace a PCB. Now, what we've done to achieve this is we've got rid of the transceiver cabinet and we've moved it down into the sensor itself. We have, instead of having analog signals as we had on the DL850, we now have smart sensors. So there's NMEA type signals coming up directly from the sensor all the way up to the electronic unit. What this means is that the transceiver, particularly the receiver, is very close to the transducers, and this gives you a much lower noise on the system, which means we need lower power going out. And by having lower power going out, we don't need a big power supply down at the bottom of the system. We can power down standard cables to the sensor. The reason we went to 2 beams was because there was a change in the standards, or the interpretation of the standards, saying that vessels over 50,000 tons had to have 2 separate systems, one for speed through water and one for speed over ground. So we made a system that would have both of these as 2 totally isolated systems within the same sensor and mountings. This is called the DL2-1, but we're talking about the DL2 at the moment. The DL2-1 has 4 transducers in the bottom, 2 going at a higher frequency for the DL1 speed through water, and 2 going at the low frequency for the DL2 speed over ground. However, the DL2 also can do speed through water, but in the DL2-1 we turn off the speed through water and use the DL1 signals. We also have a multi-frequency capability within the DL2, and this allows us to use higher frequencies for the speed through water, which gives us higher accuracy, narrower beams, which again helps us with the accuracy of the system. So the multiple frequency part. Well, we actually use the 3 frequencies within the DL2 system. We use 265 kilohertz for the speed over ground, and this pings every 600 milliseconds. If you look at the pattern on the bottom of the graph here, you see the large ping, that is the speed over ground going deeper into the water. The speed through water only goes slightly into the water. And which means we don't have to wait so long between pinging, and that means we can ping more times for speed through water than we can for speed over ground. The speed over ground has a very strong signal coming back because it comes from the seabed, which gives us a very good signal to noise ratio, which means we don't have to ping quite so often to get a good result. The speed through water is pinging into the particles within the water, and that means that you're getting a very weak signal back. So more pings gives you more signal back and more accuracy. Now, what we found was by pinging at a higher frequency, we both have a narrower beam of the system, but we also have a better accuracy because the higher frequencies tend to have better resolution. And so we do this at about 850 to 910 kilohertz, depending on the sensor. This is programmed into each sensor. So the high frequency is about twice as accurate as the low frequency speed through water, but we have both within the system. So one is redundant to the other. And generally, when we calibrate the high frequency because that is the signal that gives the best accuracy. But we also calibrate the low frequency whenever we do a C test and a manual calibration. If the high frequency doesn't work for some reason, it could be lots of bubbles, which block the high frequency worse than they block the low frequency, then the system will switch on to the low frequency instead to make sure you always have a speed through water signal. We will be making a system soon that will use both of these at the same time, and that will give us an even better improvement of accuracy. So how does the differences affect the calibration? Well, the transceiver is in the sensor, so you get lower noise and you get more stable signals, more accurate calibration based on this. The multiple frequencies, more calibrating, but done in the system. But this means that you have more to check. Generally, as I said, 2%, you don't have to check anything. 1%, normally you don't as well. But when you get problems, then you may have to check this, particularly if the problem is somehow due to bubbles, maybe a bad mounting, and the system switches into the low frequency often. You can see this by using the analysis tools that I will show you in a few minutes. Now, we have 2 beams versus 3 beams. 2 beams is a smaller sensor, although we're still on 100 millimeters, but we did this so that we could make the DL2 one. And this means that we have more calibration. The reason for this is that 2 beams don't allow you to cancel the tilt of the vessel. When you have 3 beams, you can use the mathematics to negate vertical speeds of the vessel as well. But with 2 beams, you have only got a plane going off at an angle. And as the system tilts, this will change the speed. So what we did was we put in a tilt sensor, which will get rid of the tilt of the sensor. This works well, but it doesn't get rid of the vertical water component. Now, here's a bit of theory. I'll do it quickly for those of you that are interested. Here you see the mathematics between the 2 and the 3 beam theory. Each beam can be written mathematically as 3 factors, ax plus by plus cz, where x is along the axis of the ship, y is across the axis of the ship, and z is vertical up and down. Obviously, the ship isn't going uphill or downhill, but it is going in waves, so it is going up and down. But when you're on a large vessel, it does actually look like it is going uphill because the water is being pushed down underneath the bow of the hull. And by the time it hits the transducer, which is quite close to the front of the hull, it is still going downhill, which makes the vessel look as if it's going uphill. And we can't compensate for that. To show you how that is, on 2 beams, you have AX and 0Y plus the CZ. So you've got A and C you have to get rid of. If the ship is always going horizontal, then C is also 0, and it's quite easy to work out AX. Across the ship, you have BY plus CZ. If you can cancel CZs because it's 0, then you've got BY. On a 3-beam system, you can cancel out this because you have got the extra factors in here. You've got a 3rd equation effectively. On a 2-beam system, you don't have this. So we have to calibrate this away. We have to calibrate away the Z. And what we've found is that we can do this. It is pretty constant on the ships. But on the larger ships, you have more of a vertical component than on the smaller ships. Sorry about that. Hopefully you haven't gone to sleep. We'll move on. So how this affects the calibration. Larger vessels push more water. This will cause and speed through water angles to change slightly. And so what we have added is the angle correction within the DL2. This allows us to compensate for that vertical and also for the fact that the water is maybe not pushing down directly in front of the vessel. That you have a different angle for the water than you have an angle for the ship. Different frequencies have slightly different calibrations. What we've found is that low frequency generally measures slightly further away from the vessel. It's still within the first 3 meters, but its weight is further out than with the high frequency, which is measuring closer to the vessel within the first meter, 1.5 meters. And so you will get a slightly different calibration on it. As I said, the system uses the high frequency primarily, and then switches to the low frequency if we have a problem with the high frequency. The speed over ground doesn't have a problem with this, and that is just the rotation of the sensor. So in practice, what does this mean? It means that DL2 has a slightly more complicated calibration, but what you will see generally is that this will come, you will see this as that you've got 2 installation angles. Once you've adjusted this, you don't need to think about it again. We do have, however, a high frequency and a low frequency speed through water calibration, and you only see the high frequency signal. The low frequency changes proportionately whenever you change the high frequency. This can be adjusted separately, and I'll show you how to do that just in case you need to. So if you need to check the low frequency, what you do is you go into the DL2 setup, and here you have primary frequency, which is set to high by default. When you have that set to high, what you see in your table on the diagnostics is speed to water frequency is set to high. And then the values you have on the calibration table, as you see down here, will also say high. What you can do is you can set this to low, and then you will get the low values. Then you see the table on the low values, and you can adjust that using the manual if you want to. Or you can do a C-test with the low, watching the low values. This will also adjust the high values as well. Now we are getting deep, because this isn't something that you do very often. And the reason we would normally find out that we have to do this is that a customer has complained, and that the high frequency for some reason is cutting out more often than we would expect. Sometimes in high seas, you might expect the high frequency to cut out for a short period of time and then come back. But if you have a long-term problem with your sensor, maybe it's slightly up in the valve, or maybe there's lots of welding seams close by, so you're getting a lot of turbulence, then you might find that the low frequency is operating more than the high frequency. Now, to see how the system is performing, you need to go into the logged data. And to do this logging, you put a USB stick into the system. You don't have to do anything else. You put the USB stick in, and the USB will start logging all the data that is coming into the system, both from the sensor, but also from the GPS and the gyro and everything else.
Paul, we have a question regarding this.
Okay.
One is asking if it is possible to use this data stored in the USB stick if you're changing out the electronic unit and install the calibration points again.
Yes, there is a hidden way of doing that. The reason we haven't released this very much is because when you change the box, you quite often change the software. And when you take a configuration from a lower version system, it might have changed in the higher version system. And then when you put it in, you can cause yourself a little crash on the system, and that is something we want to avoid. So generally, Although we have a function to do this, we haven't released that out because we don't want to cause more problems than it's worth. We are, if whoever's asking that, if you want to talk to me afterwards, I can tell you how it happens, but I would still prefer not to release it just at the moment. But I will put it onto the list so that we can maybe work out to get that in if that is a need in the market. And I understand why you would want that. Any more questions while we're at it? Nope.
No.
Okay, so sorry.
Oh, it's okay.
Okay. So logging data, whenever you're doing a calibration or a C test, or you've got a problem, the first thing we ask is for the vessel to put a USB stick in. You don't have to be present for them to do this. You sometimes have to fight through their bureaucracy saying they can't put USB sticks in the system. But if you can get them to do this, then we get a data set that is usually about 2 megabytes long. If it's zipped, the system will take a data set of about 30 megabytes. Older systems will then zip it automatically. The newer softwares won't zip it. The customer has to do that. The reason we don't zip it automatically anymore is because the zipping process after a while took so much computer capacity that we started getting some errors on the screen while it was doing it. So we decided to stop doing that. So you will get a data package sent by email, probably, that is 2 megabytes. And inside of that, you have a zipped up version of the data and a directory called SKIPPER. And the SKIPPER directory contains all of the calibration, the settings, and everything that the customer has done recently. These files can be looked at using a software that is on the SKIPPER website that is called GraphLog, SKIPPER analysis tools. This will load in the data. It will give you the curves of raw data, of the process data that the customer saw, and also the calibration. And in this software, you can adjust the calibration so that you can see if you can get a better set of data out for the customer. Once you've adjusted the calibration, you can send these values to the customer, and they will, if they put those in, they will get better data out of the system. It also shows a map of where the vessel is sailing, has sailed at this point. It is possible to log using the LAN port as well, but generally people use the USB because it is simpler. So once you get the USB stick, you unzip, you put it into a directory with the SKIPPER in there, and then you open the GraphLog software. You open the file that you wish to view. You may have to step through a few files before you get something interesting because they often start logging when you're alongside, and that's not very interesting. You can inspect the calibrations, and you can change the values and try again. I thought I would show you this if I manage. As I said, this can be downloaded from the website, from the software part of the website. Also, this whole course can be downloaded from the online courses part of the website. Right, if I can move this over here and then don't think that was the correct window, but in here you see what you will have in your directory. You will have a SKIPPER directory, which if you look in it, you will see downloaded setups. Here you have the serial number of the processor on your system. And going deeper into here, you have the configuration, the calibrations. All of these are text files, which don't mean very much if you look at them, except for the SKIPPER engineers. So that's why we have this tool, GraphLog, that will allow you to open the files. Now, the file you get will be a text file. It will have the name of the system, which can be changed in the system. Usually it's main or something like that, and then the number of the file. And it can quite easily be zipped, and then you will unzip it because the directory needs to have the unzipped files. So you start the software by clicking there, and it will give you a file to open. Now that one has disappeared off the window, so I will try and get onto the right one here. I can probably do it on my whole screen here. So here you see I open the demo data, and it takes a little while to load in. See, there's a bar going at the top here, and here comes the data. Now there's two windows that have come up here. This is a Google map showing where you are. This is a vessel that is in the Caribbean by the looks of it. You see these arrows on the let me just get back. The arrows are actually the current it is measuring. So it's looking at the speed over ground and the speed through water, and it's showing which direction the current is going relative to the vessel. And as you see, the size of the arrows is actually the size of the current. So as you get closer to this island here, then you see the current gets smaller. You can zoom in here and see what happened as the vessel was turning around and moving in. This is the Disney Island. Looking at the data, here you see the data as the at the moment we're on the processed. So we see this is the data that the vessel was seeing as it comes in. So this value here is the speed through water. Here we have a value from the GPS. You see it's very, very stable, only changes a bit. We can zoom in. That's, yeah. We can also look at the speed over ground isn't there at that point because it's obviously too deep. So if we zoom in here, you see that the speed to water starts coming here in. Now what we can do is we can look at the depth just to see if that verifies what we said. We can look at the DL2 depth. Here you see it's coming in at about 40 meters at that stage. But if we look at the raw data, you probably find that it was came in a bit before. No, you see it suddenly got very shallow there, 40 meters. That is quite typical in the Caribbean. So suddenly we get the speed to water because the depth is less than 150 meters and it starts. And what you should see is that the speed over ground from the DL2 follows the GPS closely, which it is doing here. What gets interesting is when you start getting into the shallower water and the vessel starts maneuvering. So if I can somehow, I lost it now. Now my scales got very strange. I'll just open the file again. Let's have a look here. Here we have maneuvering. You see that the vessel is going backwards here because this is the 0 point here. The scale on this side is the depth. The scale on this side is speed. And you see the brown is following the GPS quite nicely. If you have heading into the system, then the system acts as a kind of sat log as well and measures backwards and forwards and sideways. And you can see all of these using the external data here. So we can see heading. You can see the GPS course, GPS speed, and of course, when looking at the longitudinal here, and you can also have the transversal, which is virtually static. So you see here that the brown is following nicely the GPS. This to me says that the speed over ground is calibrated well. If we look at the transversal, and the transversal of the data as well. which is the orange. You see it's following also nicely there. Here you've got a bit of a glitch. That is probably a lot of bubbles as it's moving around. But you see, even with the rocking of the vessel, which is what's going up and down here, it is following quite nicely. So that is showing that we've got a reasonably good calibration here already. The speed to water, however, is a bit lower. And that is probably current in this case. But what you could do is, if you have a couple of sets of data taken over a few days, you can look at the speed through water. If it is always a little bit below, then you've probably got an offset on the speed through water. If, as happened on this vessel, sometimes in the files you see it's under, sometimes you see it's over, particularly if the vessel turns and you can see where you think the current is going to be coming from, then you can get an idea of how good the calibration is with regards to speed to water. And that allows you over a longer time to tweak your calibration so that the blue line is also on the GPS when there is no current. So getting back to this graph, you see here that we have the currents going in. We see the direction here. This hint at the top here is a NOAA, the American Oceanographic Institute's webpage that allows you to see the currents within the world. And here you can see here you have the North Atlantic drift, and we're looking at an island in here somewhere. Let's see if I can zoom in a bit. Okay, for some reason I can't zoom in at the moment, but if you get closer, you see the directions of the current, and you'll see clearly here that there is a current going down this way, which is what this vessel was measuring at that point. If you've got currents going in the correct direction, then you have a perfectly calibrated system. Okay, sorry, I've had it in the wrong window. Here you go. So here you can see where we are focusing on. Here you see the North Atlantic drifts moving along the Gulf Stream. And what actually happens is that the water spins around and goes down here. And that is what we can see here. We can see the current moving down. As the vessel comes out of here again, you would expect the current still to be going in that direction, so in the opposite direction relative to the vessel. So if you're always having the current going in the same directions, then you know that your system is calibrated pretty perfectly. I'll just show you the, nope, not that one. Let's go back here. So if we want to see the raw data of the system, firstly, I will get rid of that data we had before. I will keep the GPS there. We can go into the raw data of the DL2, and here we have the speed to water low frequency data, raw data. Here you see it's quite a noisy signal, and this is where averaging comes in and helps. You also see it's a bit lower. So as we calibrate, we move the curve, we smooth the curve, and we move it up. If I look at the high frequency longitudinal here, you see that it is much more stable signal. It's still lower because of the calibration, but it is a much more stable signal. You see also there's not so much dropout. Here you see dropout of the low frequency signal, whereas on the high frequency, there's a little bit of dropout here. Hopefully that doesn't correspond with the low frequency dropouts, because then it's dropout of the whole system. We can also look at the speed over ground, which of course you have nothing until you get to the right depth, and then you see it following its way down here. If I get rid of the speed through water high frequency here, you see that it's going down following the curve pretty accurately all the time, in fact, so there's not much calibration factor needed on this particular. Now, if you have a lot of noise on the system, you can look at the pitch and roll of the system. So here we're looking at the roll. If I zoom in here a bit, Here you see we're beginning to turn the vessel in this current, and there's probably some wind, and it starts rocking around quite a lot. The pitch won't do very much. You see, relative to the roll, almost nothing. But the roll of the vessel does move around. And on the GPS, you typically see the roll as an inaccuracy on speed. Because we have a tilt sensor, hopefully we shouldn't see so much of that on the speed through water after the averaging, obviously. I can have a look at the main data. So there's virtually no roll coming in there. Let's be fair and look at the same set of data. Yeah, so you're not seeing the roll in there. That has been compensated away. Now, if you have an error in your data, what you can do is you can look at the calibration. So here the calibration from the ship has been loaded in. Here you have the low frequency speed through water calibration, and here we have the high frequency speed through water calibration. You see here the two follow except for at the higher speed. Whereas on the low frequency you see the water moves away from the speed over ground much quicker. So what we can do here is we can adjust these factors. If we want, we can adjust this curve. So speed through water here, I will adjust to, it's on 13.8. I'll put it on 14.5. And then what I can do is look at the reprocessed data. In here, I can now look at the speed through water longitudinal. That's a low frequency, which was very noisy. We'll look at the high frequency. And here you see that we have the curve there. If I now, let me zoom out a bit if I can. So if you remember that, I go back to the calibration. Let's make this a bit more extreme. Let's make that 17 and that's 20. So we get a strange curve you can see here. Then we go back to the reprocessed and we repaint it. And then you see that the whole curve has begun moving down. This will depend a little bit on which speed we're at. So here you see we're actually at speed of about 8 knots. So I probably didn't adjust the right point on the table. If I make this to 13, 7, and then go back again, I can reprocess one more time, and then we see a bit more of an extreme change. So here you can adjust your curves up and down to make it match, particularly speed over ground. You can do this with full validity by this method and just give them the new values. With speed through water, you have to be a bit more careful. So that is this tool. Once you have the new calibration, you can give these values to the vessel and they can change them inside of their system using the manual adjustment. This is something that I've done for ships that are very interested in accurate data. Generally, a normal sea calibration is enough, but sometimes maybe you'll find that the ship moves into a different area. Maybe it's moving from very cold water to very warm water. If the temperature compensation didn't work properly, you might get a slight level shift in the calibration. And in this case, you could adjust it using this method. Any questions about that tool? Everybody's gone to sleep, or they understood everything? Right, so just try and get back to the presentation. problems with that. Right, hopefully I can get it now. Good. So the things that are going to affect a calibration, it's a bit important to understand what is going on there. The first thing is the currents. You will have currents in the sea, but usually you can predict where they're going to be. The captains can also quite often feel the currents, they sense it. But what you will find is if you're in a river or close to a river outlet, then you will get currents. And those currents aren't always on the surface. They can sometimes be a few meters under the water. And what you often find, or sometimes find, is that the current is actually going in a different direction under the water than it is on the surface, because on the surface it's being blown by the air, by the wind. And if you're near a river, it might be fresh water at the surface and the salt water is tidal underneath going in a different direction. So that is something you have to be aware of if you're trying to calibrate in that kind of area, or if the customer says that it's all wrong when they're in a river. It might actually be right, but they don't see it on the surface. You can also have jet streams. As the vessel turns, the design of the vessel can actually make water move a lot faster than the vessel or the current, as it is pressed down between certain elements of the hull. That has been seen on some vessels, and sometimes there's been such a long argument over it that they have run models and found that yes, this phenomenon does actually exist. So that is something to be aware of. If it happens only when you're turning the vessel, for example, then that could be something. Bubbles, obviously, if you have thrusters going, then you're going to have a lot of bubbles around. And if you have thrusters going in shallow water, the water under the vessel will be pushed around by the thruster. So you can't really rely on that for navigation. Another thing you don't always think about is wakes. If another ship is sailing around and you are in their wake, maybe even up to an hour after the sail has gone, the ship has sailed past, then there will still be some micro bubbles in the water. And this can cause interference both for echo sounders and for speed logs, particularly for the speed over ground bit. It will be like a barrier to look at the bottom. Then finally, the thing I'd like to mention is the squat effect. This is an effect that happens on larger vessels in shallow water. The pressure of the vessel pushing the water under the vessel, there's a lot of water that has to go past, and that water starts to move faster. And just like you do with the wing of an aeroplane, you get a suction effect underneath the ship, and that can pull the ship further down. There's a very interesting Discovery Channel program where they got a cruise ship under a bridge in Copenhagen by sailing the ship fast, and that made the ship sink lower into the water and allowed enough clearance for the vessel to get under the bridge. I wouldn't want to do that calculation myself, but this is an effect that is known. And if the water is moving faster under the vessel, then it will be measuring a faster speed through water than the vessel maybe expects. Even if there isn't current, you'll be making your own current. So just to mention what we're trying to do at Skipper for calibration, we're trying to make it easier. Even though the system has made it a bit more of a headache for us, we're trying to make it simpler. So what we're doing is we're working on something that is more and more automated. So we're using a method where we look at the GPS and the gyro over time. We use it as a reference, and then we are looking at the average of our values as we're going along and seeing if we can compare those and suggest to the captain some adjustments that can be made on calibration to get offsets adjusted away. We're also looking at some methods of calibrating, which mean you don't have to turn the vessel around. That is something that we're quite hopeful we might manage to do, that you have to change course. And if you're changing course, then we can get the system to do it whenever you change course, as long as the conditions are correct. So the aim of the automatic calibration that we've been working on for a number of years will be to keep you within your 2% accuracy at all times. If we can get to that, then efficiency systems can use this system as a reference, and you will get better efficiency on the ship. At the moment, we see that there are problems with turning the vessel during a sea test. That is always a nightmare, and particularly if you need to do it more than once because you want to do a couple of different speeds and then you need to do a turn on each one. So we're working on algorithms. The first one will probably come out in the new graphic EML, which comes out sometime at the beginning of next year. That one will, as you see at the bottom right hand here, allow you to make different calibrations, just as I described for different systems. You can do different speeds within the same leg. You turn the vessel and then you can do different speeds on the way back. That will allow you to do 3 calibrations if you want to, with 1 turn of the vessel, as long as you can adjust the speed on the vessel. We're also working on a new firmware for the DL2, which is even more accurate than before. It will allow us to use the speed to water from the low frequency, as well as the speed to water from the high frequency. All these improvements are being worked on at the moment. Corona has slowed things down a bit, but we are hoping to get things to start to come out in place by the end of this year, if not during next year. That's it. Any questions? No questions, so feel free to ask questions after. We'll keep this meeting open a little bit. If you want any other types of courses, there will be a course about a sales course for the Americas this afternoon at 4 o'clock. Next week, we will have an INS course for people that are doing integration and want to know how we will be doing that in the next year or so. And there'll also be a technical course, the same one as I ran last week, but at 4 o'clock in the afternoon, so that the Americas can also join in. If there's any other courses you want, then I ask that you send us an email and we will see what we can do about it. Also, if you want a meeting with us or with sales or service, then this team thing seems to work quite well. The world is getting used to it, so this is a new way that we can hold contact. Thank you for joining us today. Maybe see you this afternoon, or if not, next week, or if not, somewhere out there in the world. Thank you.